Let's start with quantum deep learning. So this may feel like a bunch of buzzwords mashed together, but really the idea I want you to take home here is that you can think of quantum circuits and quantum algorithms as objects which you can train and optimize using the exact same tools that you would use to train and optimize a neural network or a deep learning model. So as point of reference, what is deep learning? It's a subfield of machine learning that originally grew out of the study of objects called neural networks. So as an idea, we could say the following. Let's build machine learning models out of composable differentiable functions. That's a very high-level summary of what deep learning means. So in particular, those composable differentiable functions are originally neural networks. And a neural network has the following structure. It's a function f, which takes an input x and has free parameters theta. And what you do is you take that input x and you multiply it by one subset of those free parameters, which is called a weight matrix W, and then you add in another subset of those free parameters called the bias vector. And then you take the result of that and you put it through what's called an activation function sigma. And this is a differentiable transform, and it's also composable. And that's how you get multi-layer neural networks, how you get deep learning models, is you compose this simple function. Now, in order to train a deep learning model, you have to define a cost function, which is the single scalar value that it should be optimized. And typically you want the cost function to do something like compare the output of your model function when given an input with the expected answer. And you want that to be close, so you want to minimize the difference between those two things. But there's many different types of cost functions, but that's the basic idea. And then to train it, you use a trick from first year calculus, which is gradient descent. So the idea here is you compute the gradient of that cost function with respect to each parameter. So the gradient is a vector of partial derivatives, and it points in the direction of steepest descent in parameter space. So what you can do is you can iteratively update your parameters by moving them along that gradient. And eventually you should converge to a minimum. And then after you find a suitable minimum, your model can be used for classification or prediction or whatever it's designed to be used for. Now, deep learning has been tremendously successful over the past decade, and I would say there's three main reasons behind that. The first is hardware advancements. Obviously, GPUs have been very key, and deep learning requires a lot of compute to train the most powerful models. There's also workhorse algorithms. I mentioned gradient descent, and there's also the backpropagation algorithm, which is used to compute the gradients. And finally, one thing that has really enabled the field to take off is the ability for users to rapidly experiment, prototype, and try out different ideas using very user-friendly software, which a few of them you may have heard of. So I want to actually say that there's something deeper than deep learning. It's called differentiable programming. This is something that deep learning falls under, but actually you can think of it a bit more broadly. So the basic idea behind differentiable programming is the following. Any code should be trainable, not just machine learning models. Okay, so how does a differentiable program differ from a deep learning model? Well, the idea here is that your function is not just a neural network, but it's arbitrary code. It should be numeric code, it should be differentiable because we want to train it, but it could be code, for instance, written in Python. Again, you want to define a cost function. This can actually look very similar to a deep learning cost function where you compare the desired results to the results achieved with a particular set of parameters and then tune the parameters. And again, we can use gradient descent as a rule for optimizing this cost function. And after optimization, this code should now be very well tuned to specific purposes, which may go beyond what a machine learning model is meant to do, which is usually to make predictions or to fit functions. So this particular example here I've taken from the Python library AutoGrad, where their differentiable program is actually a fluid simulation, and they're optimizing it to produce some particular configuration here, a peace sign, you can see. Differentiable programming is quite broad. There's a lot of ideas now starting to emerge that are maybe less aligned as deep learning and more aligned as differentiable programming. So I just list a few here. Neural Turing machine, this is basically a neural network type model that has access to an external memory. There is neural ordinary differential equations where you're not optimizing a neural network, but you're optimizing a solver to a differential equation. other things like physics or graphic engines. And as well, you might have seen this Deep Dream a few years ago. And this is actually something that got inspired me to get into machine learning. The idea here is that you have already trained a predictor, to classify whether you have a particular object in your image, and then you take the input image then as your trainable object, as your object that can be optimized, and you freeze the predictor's weights, you freeze the predictor's training, and you just train the input. And you can say, give me the image that looks most like towers, or has the most towers in it, or best represents towers, or best activates the tower classification. And you end up with these really weird, crazy images. And this is starting to bleed out of neural networks and more into differentiable programming, where the thing you're optimizing is no longer a model, but the thing you're optimizing is the image itself. So there's very friendly software for differentiable programming. These things you might have just assumed are used for machine learning, but they're extending more and more to broader things. And there's covering Python typically, but also Julia libraries. And the very nice thing that these libraries do for you is something called automatic differentiation. These handle all the optimization parts for you. So you can build your computation, you can build your program, and then these take care of training it for you, in particular computing the gradients. So now we're talking about quantum computing. We want to connect that to deep learning. So very basically, quantum computing, you have a set of quantum systems which are manipulated via a series of gates. We call this a quantum circuit. And the power of quantum computing comes from its inherent special ability to interfere complex amplitudes in a very high dimensional space. So it's not just the ability to work in a high dimensional space, but it's actually the ability to do interference in that space. Now, the basic structure of a quantum circuit is you start with some initial state, psi. Typically, this is an all-zero state or a ground state. Then you execute some particular unitary transformation, call it U. And U can be broken down into a sequence of individual gates. And this is the bulk of your circuit. And then at the final step, you measure some observable quantity, let's call it B. And this is the step that your quantum state is converted into classical information, which is the measurement result. So the key point I want to emphasize about quantum circuits is that if you look at the average value of your measurement results, this is also called the expectation value in quantum theory. If you look at the expectation value of your results of measuring the observable B, then there's this nice formula called the Born rule, which tells you exactly what that looks like mathematically. And it basically is just an inner product of two vectors, or a product of matrices in vectors. So psi, if you're not familiar with the notation, psi in these, it's called a ket, and it's just a vector. And then the U, parameterized by theta, U is a matrix, and it's just multiplying that vector. B, again, is represented as a matrix. It just multiplies the thing to its right. U dagger is the adjoint gate, or the adjoint unitary of U, so the complex transpose. And then finally, you have, again, a psi, but the direction is reversed, and this is now a dual vector. So in the end, this is just a kind of inner product, and it gives you a scalar value. And it's a very nice formula. But it's all just linear algebra in a very high dimensional space. Now, the important point I want to emphasize is I put this value theta in for the unitary transformation. So what that means is that the final expectation value is a function of theta, which are the gate parameters. And it's a continuous function as well, since it's just linear algebra. So this allows us to start thinking about quantum differentiable programming. As I said on the previous slide, the Born rule is just a linear algebraic expression, so it's differentiable, which means that all the ideas of differentiable programming, that we should be able to train an object using gradient descent, all of this applies to quantum circuits that are parameterized unitaries. So we have a circuit, and it spits out some function which depends continuously on parameters theta. And we should be able to train that function just like we would train a neural network. So this is cool because it opens up some possibilities for how you can connect quantum computing devices with machine learning. One perspective is to use quantum devices for machine learning. So you use a quantum device as to make a classifier or something. The other way you can think of it is actually to use machine learning tools and differentiable programming tools to better understand quantum systems and quantum computing. So this is what I would call the machine learning for quantum perspective. You're using the tools of machine learning and you're applying them to quantum computing circuits. So this is kind of a duplicate of the slide that I showed earlier, but now it's how can quantum machine learning be successful rather than how deep learning was successful. So it's a really cool point right now because we're starting to see those hardware advancements. We have devices which are getting harder and harder to simulate and are doing more and more interesting things. As I'll get to a bit later, we do actually have also some workhorse algorithms we can rely on, and these can be largely ported over from deep learning. And as well, there's an emerging suite of software devoted to quantum machine learning and differentiable programming of quantum computations. So one thing is PennyLane, which is done by my team at Xanadu, but also we have TensorFlow Quantum, we have a Julia library called YAO, and there's a library developed by the University of Toronto group called Tequila. And they're all focusing on this core idea that quantum computations are differentiable programs. So that's the story so far. It's pretty cool. It says that the ideas of deep learning are very nicely ported over to quantum circuits. But there's still a missing piece of this story that I haven't really explained yet, which is if we want to train quantum computers like neural networks, we want to use gradient descent. We need a way to compute the gradient. But as I said, quantum computers have this special capability of interfering complex amplitudes in large dimensional spaces, which is in a lot of cases hard to simulate or emulate classically, or basically intractable to do so. So if we have a computation and we have a circuit that is intractable to evaluate on a classical device, how could we possibly compute the gradient of that? So we not only need to evaluate the function that's coming from the circuit, we need to evaluate the gradient of that function. How can we do that if the circuit itself is classically intractable?